Alright, time to talk about one of the coolest celestial events you can witness. When the sun disappears in broad daylight. Imagine it's noon, bright daylight, and suddenly the sun starts to disappear. No one had science back then, so many cultures believed a giant beast was eating the sun. Scary, right? Luckily, today we have science on our side. So, what's really happening? The moon is photobombing the sun. It passes directly between Earth and Sun, casting a shadow on Earth. So, if you are standing in just right the spot, you will see the sun disappear completely or partially. Whether you see a total or partial eclipse depends on where you are standing. Sometimes your friend in another city sees total darkness while you just get a sun with a chunk missing. So let's look at this total solar eclipse. The sun's brilliant outer atmosphere, the corona, shines only when the bright disk is hidden. This is what people travel thousands of miles to see. It's called totality and it only lasts a few minutes. Next up, how is this even possible? The sun is 400 times bigger than the moon. So let's explore the trick of angular diameter in our next slide. So let's dig into the cosmic math behind eclipses. Why does the moon, tiny compared to sun, but manage to block it so perfectly? Here is a cosmic coincidence. The sun is way bigger than the moon, but it's also way farther from Earth. So to us, they look about the same size in the sky, about 0.5 degrees. That's why solar eclipses work so perfectly. So when you order pizza, you ask for a 16-inch pizza. That is linear diameter, right? But if I hold that pizza at arm's length, it looks smaller, right? That is angular diameter. It depends on both the size and distance. So this diagram helps make sense of it. The farther an object is, the smaller the angle it makes in your view. That's why a car across the street looks smaller than the one next to you, even if they are the same size. Now this formula is like a super tool for astronomers. You will use it again and again in astronomy. If we know how big something is and how far away it is, we can calculate how big it looks from here. So in this small angle formula, you must always use the same units for distance and linear diameter. Remember to use the same units. So this version of the small angular formula uses arc seconds as the unit of angular diameter. And the constant 2.06 times 10 to the power 5 in this formula is the number of arc seconds in 1 radian. So first, let's do a simple exercise. Now using the simple angle formula, first let's find the angular diameter of the moon. Because the moon's linear diameter and the distance are both given in the same units, kilometers, you can put them directly into the small angle formula because the kilometer units will cancel out. So here, for the linear diameter, you can use 3480 kilometer, it's given. And the distance, it is given, the average distance from Earth is 384,000 kilometers. So we can use the kilometer units because they are same for those distances, so they will cancel out. Now when you do the calculation, you will find that the angular diameter of the moon is 1870 arc seconds. Now if you divide this number by 60, then you get it in arc minutes, which is 31 arc minutes. And again if you divide this number by 60, you get about 0.5 degree. Next, let's calculate the angular diameter of the sun. So the sun has a linear diameter of 1.39 times 10 to the power 6 kilometer. and its average distance from Earth is 1.5 times 10 to the power 8 kilometer. Now if you put these numbers into the small angle formula, you will find that Sun has an angular diameter of 1910 arc seconds, which is about 32 arc minutes or zero point 0.5 degrees. So look at this. Even though the Sun is massive compared to Moon, its angular diameter ends up nearly same. That's why you can sometimes get a perfect eclipse. The Moon is just the right size to cover the Sun from Earth's point of view. There's a common misconception. You have probably seen a full moon rising and thought, wow, it's huge. But that's just a trick your brain plays. Its angular diameter has not changed at all. The same moon, same size. Now we are going to dive into how the moon's shadow interacts with Earth and why eclipses are only visible in certain places. Let's begin by looking at this image. So during a solar eclipse, the moon blocks sunlight and casts a shadow on Earth. So that shadow has two parts. The umbra, where the sun is totally blocked, and the penumbra, where it is only partially covered. And if you are in the umbra, you will see a total eclipse. And if you are in the penumbra, you only get a partial eclipse. But that total eclipse doesn't cover the whole world. The umbral shadow is very small, only up to 270 km wide. And it moves fast, sometimes over 1800 km per hour. That's why eclipses don't last long or happen everywhere. And if you are lucky enough to be in the path of totality, that narrow strip across Earth, you will see the sun go completely dark. Just outside that path, you will see only a partial eclipse. Now this satellite image shows the moon's shadow from space. Can you see that dark spot? That's the umbra moving across the Earth during the 1991 eclipse. Imagine standing right under that shadow. That's what eclipse chasers aim for. Okay, so now you know how the shadow moves. But what happens when the moon is not quite big enough to cover the sun? Let's go to the next slide to find out. The moon is not always the same distance from Earth. When it is closer, that means at perigee, it looks larger. And when it is farther, that means at apogee, it looks smaller. This changes how much of the sun it can cover during an eclipse. Even a smaller change of 5.5% in the moon's apparent size can make the difference between a total eclipse and an annular eclipse. Now, if the moon looks slightly smaller than the sun, can it fully block the sun? Look at the figure A here. This shows the effect of the moon's changing size, apogee versus perigee. So the moon is not always large enough to completely cover the sun. And the Earth-Sun distance changes slightly throughout the year. So this makes the sun appear a little larger or smaller in the sky. So these small changes can make a difference during an eclipse. Sometimes the moon can't fully cover the sun even when perfectly aligned. And this diagram shows why the moon's shadow falls short, leaving a ring of sunlight visible. That means the umbra of the moon does not reach Earth and the eclipse is annular. That means we can see a ring of the sun's disk around the moon, which we call as annulus. Now, if the moon's shadow doesn't reach Earth, we see a bright ring of the sun around the moon. That's what we call an annular eclipse. Because total eclipses are rare at a fixed location, some people travel around the world to see them. So these eclipse chasers plan years in advance to be in the path of totality. So here's an actual annular eclipse. Notice the bright ring of the sun around the moon. It is exactly what observers see in this type of eclipse. So previously we saw annular eclipses, which happens when the moon is too small to completely cover the sun. Now we are going to look at total solar eclipses, where the moon fully blocks the sun and reveals the sun's outer atmosphere. So this sequence shows how the moon gradually covers the sun. At first, you see the moon nimbly in the sun's edge. This is the start of a partial eclipse. Even though the moon is covering part of the sun, it is still bright outside. Look carefully. More and more of the sun disappears minute by minute. How long do you think it will take before the sun is completely covered and totality begins? Think about the change in light and imagine being there. So during the partial phases, the moon gradually covers the sun over roughly 1 to 2 hours. The sky is still bright until the last silver disappears. And then totality begins in just a few seconds. Once totality begins, darkness falls quickly. So day becomes night for a few minutes. Now with the bright surface gone, the corona appears, a pale wispy glow around the moon. Now look at the ruby chromosphere and ring prominences. They are only visible during totality. The chromosphere is a thin, bright layer above the sun that looks pink during a total eclipse. And prominences are huge eruptions of gas. So during totality, these features become visible along the edge of the moon, giving the sun a dramatic, colorful outline as in this figure. Now so far we have looked at the sequence of partial phases leading up to totality and how the sun's atmosphere like the corona, chromosphere and prominences become visible. Next, let's focus on what happens at the very end of totality and the famous diamond ring effect, which only lasts a few seconds but is one of the most striking sights in astronomy. So as totality ends, sunlight quickly returns and the sky brightens again. So the corona and the chromosphere disappear. Imagine how fast the landscape changes from near darkness back to daylight in just seconds. Even though it feels magical, totality doesn't last long. Most eclipses give only 2 to 3 minutes of darkness at a location. This is why eclipse chasers travel around the world to catch total eclipses. They don't happen often in one spot. So at the very beginning or end of totality, a tiny bit of the sun can shine through lunar valleys. So this creates a brilliant diamond on the silvery ring of the corona, and it lasts only a few seconds. So timing is everything. Imagine seeing a sparkling ring in the sky for just a moment. It's one of the most breathtaking sights in astronomy. Remember, you can only safely look at the sun without protection during totality. Otherwise, always use eclipse glasses. So in the next section, let's learn how to safely view an eclipse, what equipment to use during partial and total phases. So before we had solar telescopes in space, scientists would journey to the path of totality to study the faint corona visible only for a few minutes. Think of the effort and planning involved. Even though we can observe the sun every day with the space instruments, people still travel to remote places for the sheer excitement of seeing totality. It's not just science, it's an adventure. Now during partial phases, part of the bright photosphere is still visible, remember? Even a tiny silver can burn your retina instantly. Eclipse or not, looking at the sun is dangerous. There are some filters that block visible light, but they let infrared heat through. So that heat can seriously damage your eyes. Therefore, remember, even dark filters are not always safe. So you might think sunlight is only dangerous during an eclipse, but it's always dangerous. I know the eclipse just tempts people to look at it directly. Now, the simplest way to watch a partial eclipse safely is to project the sun's image through a pinhole onto a second card. The farther the cards, the larger and dimmer the sun's image. And also we can use natural pinhole projections. That means the tiny gaps between leaves under trees act like natural pinholes, projecting crescent-shaped sun images on the ground. Right before totality, this creates an eerie effect of many small crescents on the ground. And as I said in the previous slide, once the sun is completely covered, the corona is visible. And then it is safer to look with the naked eye. So this totality is actually fainter than a full moon. So your eyes can adjust safely. Now you know both the thrill of seeing an eclipse and the safety precautions needed. So with this we conclude the chapter 3. Alright, we have covered a lot about the moon and eclipses. Let's pull everything together with a quick summary. So the moon orbits Earth once a month and spins on its axis just right so that the same side always faces us. That's why we never see its far side from Earth. And as the moon goes around, we see different amounts of the sunlit half, and that creates the familiar faces. When the lit portion is growing, we say the moon is waxing, and when it is shrinking, it's waning. And a full cycle of phases takes about 29 and a half days. We call it the synodic period. So compared to the stars, the moon actually finishes its orbit in only 27.3 days, the sidereal period. That difference happens because the Earth is moving around the sun, so the moon has to catch up to line up again. Next, we learn about lunar eclipses. So sometimes during a full moon, Earth gets directly between the sun and moon. That's when we see a lunar eclipse. And if the moon goes completely into Earth's darker inner shadow, the umbra, we get a total eclipse. And only if part of it slips into the umbra, it's partial. And if it only passes through the outer shadow, the penumbra, it's called the penumbral eclipse. Next, during a total eclipse, the moon doesn't disappear. It glows a coppery red. That's because sunlight bends through Earth's atmosphere, scattering the blue light, and what reaches the moon is a blend of red and orange light, like every sunrise and sunset around the globe being projected onto it. And the solar eclipse is the opposite. It happens at new moon, when the moon moves between us and the sun. So if you are in the right place on Earth, the moon's shadow sweeps over you and suddenly the sun is covered. So when the moon is close enough, it can block the sun completely, giving us a total solar eclipse. But if the moon is farther away, it looks a bit smaller and leaves a glowing ring, an annular eclipse. Many people outside the main shadow just see a partial eclipse. So during a totality, when the sun's brightest face is hidden, we can finally see its outer layers, the corona, the chromosphere, and a giant flame-like prominences. Sometimes right at the edge of totality, the sunlight peeks through valleys of the moon, creating the famous diamond ring effect. It's breathtaking, but remember, except during totality, it is never safe to look directly at the sun. The safest way is to use indirect projection, like with a pinhole or eclipse glasses. So that's the big picture of how the moon changes and how both lunar and solar eclipses happens. Now, before we move on, I would like you to go through the practice questions and answers posted with this section. Take some time to think through them on your own first. Then check the answers to see how you did. And don't forget to complete the homework for this chapter. This is where you will really lock in what you have learned today.